Yes. So I was discussing arbitrary union of this theorem. Arbitrary union of open sets is open. Union of open sets is open. So how to prove this? So what was arbitrary union? Last day I tried to explain. Means we have any collection of open sets. So we have seen that collections can be very large as well. Okay. Not only countable collection, there can be uncountable collections also. Okay. So something like this, say A1, A2, A3. Okay. This is called a countable collection. So where the indices are from a countable set. Okay. So this index is a subscript. If the indices are from a countable set, okay, then the collection is said to be a countable collection. Okay. And it may happen that the indices are from an uncountable set. A alpha such that alpha belongs to closed interval 0, 1. Okay. You may have collections of this type also. For each alpha inside 0, 1, A alpha is a set, open set. So this is an uncountable collection. Okay. It's not countable. This is an uncountable collection of open sets. So there are open sets like A0, then A0.00001. Okay. We cannot list it. So it says that even if there is an uncountable collection, if you take the union, it is going to be open. Okay. So arbitrary union of open sets is open. Okay. So how we write an arbitrary collection of open sets? We will write it as this: AI such that I belongs to capital I. So where capital I is the index set. Okay. So here in this case the index set is what? This collection I can write this one as set of AI such that I belongs to set of natural numbers. So here for this collection the index set is n. Okay. Set of natural numbers. And for this collection the index set is closed interval 0, 1. So in general I denote arbitrary collection of open sets as this. And a collection of AI such that I belongs to capital I. Okay. So how do I prove this? So prove is very simple. So we start with an arbitrary collection. So we have denoted open sets by G. So let us write this one as G. Let Gi such that I belongs to capital I be any collection of open sets. Okay. So it is itself a set. Be any collection of open sets. Open sets in R. Okay. Where, so let us write where, what is I? Where I is a non-empty index set. Non-empty index set. Index set. So if we take empty collection, we are taking a non-empty collection. Even for empty collection also this union is open. For empty collection, the union of empty collection of sets will be phi itself. There are no collections. So phi is always open. So we consider just a non-empty index set. Okay. I is a non-empty index set. Okay. So next I have to show that this is open. Okay. Let G equal to union of to show G equal to union of I belongs to capital I of Gi. Okay. Is open. Okay. I have to show that this collection is an open collection. Sorry, this set is an open set. Okay. To show this is an open set. So how to show? So open set is either empty or for each element inside that set we will get an open interval which contains that element and is contained inside this. Okay, these are the requirement for open sets. Either it is empty, it can be empty also. Okay, empty with the so it will be empty if all the members, all these members are empty. Okay, what is this symbol? This symbol is nothing but this one. Okay, suppose I write A1 union A2 union A3 union A4 union dot union say A100. Okay, so this is the short form of writing. So I can write this one as AI such that I belongs to this set 1, 2, 3 up to 100. Okay, the index set. Isn't it? This is the short form of writing this union. Instead of writing A1 union, A2 union, A3 union, A100, we will just write it union I belongs to this index set. Okay, indices will come from this. So that is the system. So here also the same thing. Union of I belongs to capital I of GI. Okay. So we have to show that this is open. So if GI is equal to 5, it may happen that if GI is empty. If GI is equal to 5 for all I in I, okay, then G is itself equal to 5. If all sets are empty, if all the sets are empty, okay, it may happen because this is an arbitrary collection. Okay, so somebody may give you a collection of 100 open empty sets. So even then, the union is open. Okay. So if GI is 5 for all I, then G equal to 5. Okay, which is open. Which is so we have considered a particular case. So let G not equal to 5. Okay. G is not equal to 5. Okay. That means at least one of the GIs is non-empty. Right? G not equal to 5. That is at least one GI is non-empty. Let G not equal to 5. That means at least one of the members is non-empty. Okay. So what we can do is we can take one element inside G. Okay. Let X belongs to G be any element, be any point. So what is the definition of open set? For each point inside this set, we should get an open interval which contains X and is also a subset of G. Okay, this should happen. For each X inside G, we should get an open interval which is contained in this set. Okay, so this is what we will try to think. So let X belongs to G be any point, then X belongs to union of I belongs to I of Gi. X belongs to the union of this. G is nothing but union of this. So if X is there in the union, then X should be there in at least one of the sets. So something like this, X belongs to A union B. From this, what you write? X is in A or X is in B. Means X is there in at least one of the sets. If it is not there in any of the sets, it cannot be there in the union. Okay. So we have X belongs to union of this. So from this, in the next line I can write implies X belongs to GI for some I inside capital. Okay. Right. X is there in the union. That means X is there in one of the sets. Okay. It may be there in more sets, but at least we know it is there in one of the sets. At least. So from this line I can write this. X belongs to GI for some I inside capital. Okay. So from there, in the next line I can use the fact that GI is open. Each GI is an open set. Let GI be a collection of open sets. Let's see. First line, open sets. Let's see. Okay. So we have an element inside GI, and GI is an open set. Okay. But GI is open. Okay. GI is open set. Okay. Open set in R. So what is the definition of open set? So for each epsilon, means for each element here there exists an open interval. Okay. There exists. So but GI is an open set in R. So there exists epsilon greater than 0 such that x belongs to this interval. Okay. X minus epsilon to x plus epsilon. Okay. And this is a subset of G. Okay. Or I had written alternate definition of open sets last time. There exists an open interval which contains x equal epsilon plus x. I can use that also. Okay, without epsilon also we can do it. Okay. So just start this part. We'll do it using the alternate definition. Okay. So there exists an open interval. There exists an open interval. Say what I to index and millennium. Okay. There exists an open interval. Say Ix. This I is again confusing. The same I. There exists an open interval, say J. Okay. There exists an open interval J such that X belongs to J and this is a subset of Gi. Okay. This happens. Okay. If a set is an open set, then for every element in that set, there should exist an open interval which contains that element and is also contained in Gi. Okay. So from here I can write x belongs to J and this is a subset of Gi, but Gi is again a subset of the union. Union of I belongs to I of Gi. This also is true. Okay. Gi is one of the members of this union, of this collection. Okay. I have used this result. A is always a subset of A union. If you add another one, A is always a subset of A union, B union, C. Okay. Whatever union you take, A is always a subset of that. Okay. So this is a particular member of this collection. So this is always a subset of the whole union. Okay. So X belongs to Gi, X belongs to J, subset of this. Okay. So that means ultimately I have got an open interval. That is, I have got an open interval which is a subset of G. That means G is an open set. Okay. I have started with an element of G and I have got an open interval which satisfies this. Okay. So G is an open set. So we can write it here. So since X is arbitrary, so G is an open set. So the arbitrary union of open sets is open. So the result is proved. Just have a look if there is any doubt. X is in the union of this, so X will belong to one of the members, Gi for some I. But Gi is an open set in R, so there is an open interval J such that X belongs to J, which is a subset of Gi. But Gi can be written as a subset of union of this. So X belongs to J, which is a subset of G. Okay. So G is an open set. Okay. So this is the truth. Arbitrary union of open sets is open. Okay. Next. So another exercise we can try that intersection of open sets is also open. Intersection of two open sets is open. Theorem also we can try. Intersection of two open sets. Intersection of two open sets. Open sets in R is open. If we take the intersection of two open sets, we get an open set. So how to prove it? Similar to the earlier one. So we start with two open sets like G and H. The two open sets. The two open sets. Open sets in R. So if G intersection H is phi, if this is an empty set, then it is open. Then G intersection H is open. So let this be non-empty. So let G intersection H is non-empty, and let X belongs to G intersection H. Be any element, okay, or any point. Okay. Starting as this. We start with any two open sets in R, and if their intersection is phi, then this is an open set because phi is always open. Okay, empty set is always open. We have already done. Empty set is an open set. So let this be non-empty. Suppose this is non-empty set, and let X belongs to G intersection H be any point. Okay. Let this be any point. Then what we do? Okay, so after this, we have to write. So this implies, so X is a member in the intersection. So it is there in both the sets. X belongs to G and X belongs to H. Okay. X is a member of G also and X is a member of H also. But what are these G and H? G and H are open. G and H are open. Open in R. Okay. So now we will use another definition, the first definition that I gave. So there exists epsilon 1, epsilon 2 greater than 0 such that X belongs to X minus epsilon 1, X minus epsilon 2, okay, which is a subset of G, and X belongs to X minus epsilon 2, X plus epsilon 2, which is a subset of H. Okay. There exists an open interval of the type this, which is a subset of G, which is a subset of H. Okay. So this is the first definition I gave you. Oh yes, it will be X plus. X minus epsilon 1 and X plus epsilon. Yeah, correct. It is correct. X minus epsilon 1, X plus epsilon. Okay. That means I have got a open interval with center at X, okay, and radius epsilon, okay, epsilon 1, which is a subset of G. I may get an open interval of radius epsilon 2, which is a subset of H. Okay. So which interval should I select so that it is a subset of both G and H? Which epsilon should I select? X minus epsilon 1, X minus epsilon, X plus epsilon, this is this, and epsilon 2 is suppose here, then this is this. So which interval will be a subset of both the sets? The smaller one. We can guarantee that the smaller one will be a subset of both the sets. Okay, right? If epsilon 1 is this and epsilon 2 is this, okay, then also the smaller one. Okay. Smaller one will be a subset of both the sets. Okay. This is a subset of G, this is a subset of H. The larger one, suppose this is a subset of H. Okay. So the smaller one is a subset of both the sets. Okay, because the smaller one is already, suppose this is the smaller one, then we already have X minus epsilon 2, X plus epsilon 2. This is already a subset of the larger interval. Minus epsilon 1, X plus epsilon 1. This is already a subset of G. Okay. Here this is a subset of G. Okay, and we already know that this is also a subset of this is a subset of H also. Okay. So this is a subset of the smaller one is a subset of both the sets. Okay. So it will be a subset of their intersection. So I will take minimum of epsilon 1 and epsilon 2. So let epsilon equal to minimum of epsilon 1, epsilon 2. Okay. Then X belongs to X minus epsilon x plus epsilon is a subset of G, and x belongs to x minus epsilon to x plus epsilon, which is a subset of H also. Okay, it is a subset of both the sets. So it will be a subset of their intersection. A subset of both the sets. So this will be a subset of their intersection also. Therefore, x belongs to x minus epsilon, x plus epsilon, subset of G intersection H. Okay. So we have got an open interval centered at x, which is a subset of G intersection H. Okay. So I can say, since x is arbitrary, so G intersection H is open. So I have proved that the intersection of two open sets is open. So, sometimes we use that definition, this definition in terms of epsilon, and sometimes we use the definition in terms of any open interval, okay, whichever is easier to use. So we can extend this to a finite collection of sets also. Suppose if you have finitely many open sets, okay, then also their intersection will be open. Okay, we can extend this. So the next result is finite intersection of open sets is open. Next result is not only two, if we have finite number of open sets, say 100, 200, million open sets, then also means the number should be known, how many are open. Then also the area is open. Okay. So we can do it this way also. When we will get this intervals of the type x minus epsilon I to x plus epsilon I, which is a subset of say Gi, and then take the minimum, epsilon equal to minimum of epsilon I. Okay. This way also we can do, or we can do it using induction. Using induction also we can do it. So both methods are correct. Let me just check. So this is the theorem. Finite intersection of open sets is open. So if the question is this, you consider a finitely many collection of open sets, okay, not two. So proof is this. So let us write this using Gi such that I. So since it is finite set, we have already done the definition of finite set. Any finite set has a bijection from the set to the set of first n natural number, 1, 2, 3 up to n. So any finite collection we can denote it this way: Gi such that I goes from 1 to some n, okay, some value. Okay. Let Gi such that I goes from 1 to up to n be a finite collection of open sets. Finite collection of open sets. Be a finite collection of open sets. Okay. So I have to show their intersection is open. Okay. So let G equal to intersection I goes from. So I will write it this way. Intersection I goes from 1 to n of Gi. Okay. Finite intersection. So I could have also written it as I belongs to 1 to up to n, but that will require more space here. It will look clumsy. So that's why I have written like this. I equal to 1 to n Gi. Okay. So this means actually G1 intersection, G2 intersection, G3 up to Gn intersection Gn. Okay. So let G equal to this. So if this is phi, it may happen that this intersection is phi. So So if G equal to 5, then G is open. আমরা আর কিছু করার নেই। If G is 5, then it is open. So let G not equal to 5. Let G not equal to 5. Okay. And let X belongs to G. Be any point. Okay. Be any point. Okay. So we have to find an open interval which contains X and is also inside G. So this means X belongs to intersection I goes from 1 to n of Gi. Okay. What does this mean? This means that X belongs to Gi for all I equal to 1 to up to the minimum. X is there in the intersection. That means X is there in every set of this set. So, but each Gi is an open set. So I can apply the definition of open set now. So each Gi is open, but each Gi is open. So there exists. So for this G1, there will exist one epsilon 1. Okay. For G2, there will exist one epsilon 2. Okay. So for Gi, in general, for Gi, there will exist one epsilon I. Okay. Greater than 0. So there exists epsilon I greater than 0 such that X belongs to X minus epsilon I to X plus epsilon I. This is a subset of Gi. So there exists epsilon I greater than 0 such that X is there in this subset of this for all I 1 to up to. Okay. So for G1 there is epsilon 1, for G2 epsilon 2. That means ultimately I have got a collection of intervals. Say for G1 suppose I have got epsilon 1. Okay. This is X minus epsilon 1 to X plus epsilon 1. Okay. For G2 maybe I have got a smaller epsilon. Okay. Say X minus epsilon 2 X plus epsilon 2. Okay. For G3 maybe I have got a very large epsilon. Okay. So these are random. It is not necessary that epsilon 1 is less than epsilon 2 or epsilon 2 is less than epsilon 1. Okay. These are random. Okay. So but ultimately they are symmetrically distributed about X. Okay. So that way I have got. So whatever it is, the smallest radius that we take will lie inside all this collection. The minimum one. Okay. So I will take epsilon equal to minimum of epsilon I. Okay. Then the smallest one, this will be a subset of everything. Okay. That is what we will do. So let epsilon equal to minimum of. So since this is a finite collection, I can talk about minimum. Okay. If it is an infinite collection, I cannot talk about minimum. I talk about infimum. Okay. So in that case, infimum may not exist. Since it is a finite collection, infimum will exist. Always. So minimum of epsilon I such that I equal to 1 to up to. Okay, so there are finitely many numbers. So we choose the smallest number out of this. Okay. Right. So let epsilon equal to minimum of epsilon I such that I goes from 1 to up to n. Okay. Then we can write. Then X minus epsilon to X plus epsilon. This is always a subset of X minus epsilon I to X plus epsilon I. Subset of Gi for all I. Okay. For all I equal to 1 to 2. Okay. Means this interval, this is a subset of this one for all I. Okay. Because we have taken the smallest radius. Okay. X belongs to this. X belongs to this. And this is a subset of this, and this is again a subset of that by that for all I. So this is a set which is a subset of every Gi. Okay. So from here I can write X belongs to X minus epsilon, X plus epsilon, which is a subset of Gi for all I equal to 1 to 1. Okay. So it is a subset of every such set. So it is a subset of their intersection. x minus epsilon to x plus epsilon, subset of intersection I goes from 1 to n gi. Since it is a subset of every set, so it is a subset of their intersection also. Okay. And what is this? This is nothing but g. So ultimately, I have got for each x in G, I have got an open interval which is a subset of G and also contains the point x. So G is an open set. So from here I can come to conclusion that G is open. Therefore, since x is arbitrary, so G is open set. Okay. Okay, so this is the proof. Now please try to practice. Practice for color. Okay, so we have done finite collection. Intersection is open. Next we will see that if you take an infinite collection, arbitrary collection of open sets, then their intersection cannot be open. Okay? So we will give an example for this case. Right? If you take a collection of infinitely many open sets, then the intersection may not be open. So how to do that? So we will write this as a note. So note that arbitrary intersection of open sets need not be open. Of open sets need not be. Arbitrary intersection of open sets. This may not be open. So what is an example? An example is this. Suppose you see if I take the intersection of this thing, say this is like minus 1, minus 1. This is 1, okay. Say minus 1, 1, and then I take an open interval minus 1, 1. Okay. Next I take minus half to half, minus half of this open interval. Okay. What is the intersection of these two? Minus 1, 1 intersection with minus half. What is this? It will be same as minus half because this is a subset of this. And this is a subset of this. Next I take say minus 1/3 to 1/3. Okay. And then I take intersection. Okay. Intersection with this and then intersection with this. Okay. What is this? It will be minus 1/3 to 1/3. Next again, so you keep on doing this. Okay. Minus 1/4, 1/4. Okay. Minus 1/5, 1/5. Okay. You consider this sets and keep on taking intersection. Okay. Infinitely, continue. Okay. Magnify this. Magnify kori aro continue. Okay. Suppose after magnification it comes out to be something like this. Just say minus 1 by 10 to the power 20, 21. This is say 1 by 10 to the power 20, 21. Something like this. You can go further. Keep on taking intersection. What is the intersection? What will be the intersection? So it seems that intersection is 0. Okay, actually intersection will be 0. Okay. If you take the intersection of all these sets, intersection n belongs to natural number of minus 1 by n to 1 by n, then the only element which belongs to this intersection is actually 0 only. Okay. And this is not an open set. It cannot contain any interval. 0 is a singleton set. For open interval, for open set, for every element we should get an interval which is inside, open interval which is inside that set. So singleton 0, it cannot be open set. Okay. Because it contains only one element, it cannot contain any interval. Okay. So this intersection is actually singleton 0. Okay. Keep on taking an intersection. Gradually the things will go closer to each other. Okay. You can actually prove this. This is 0. Okay. So we will write this example. So intersection of, if we take infinitely many sets, their intersection may not be open. Okay. Not an open set. So the example is this very simple example. So let Gn equal to open interval minus 1 by n comma 1 by n for all n inside capital N. Then each Gn is an open set because this is an open interval. Then each Gn is an open set. Each Gn is an open set. But if I take the intersection, intersection n belongs to natural number of Gn, which is equal to intersection of n belongs to natural number minus 1 by n to 1 by n. This is nothing but singleton 0. Okay, it is a set containing only the point 0. Which is not open, which is not an open set, which is not open. As it doesn't contain any interval. It doesn't contain any interval. If a set doesn't contain any interval, then we can guarantee that it's not an open set. But if it contains an interval, we cannot guarantee. Okay. Then we have to check further. So if it doesn't contain interval, we can easily say it's not an open set. It doesn't contain any open interval. Okay, how to show that this is singleton 0? How can you show that this is singleton 0? Just, you don't have to write anything, just see how we can prove it actually. Okay. So suppose there is a non-zero element here, okay, positive number. Okay. Suppose that epsilon belongs to this intersection. Okay. Epsilon greater than 0. Epsilon is a positive number. Suppose there is a positive number which belongs to this intersection. Okay. 1 by n to 1 by n. Then what will happen? Then we will get epsilon lies between minus 1 by n to 1 by n for all n belongs to natural number. Okay. Now, this is the meaning. Epsilon is in this intersection. That means what? Epsilon is a positive number which lies between minus 1 by n to 1 by n for every natural number n. Okay. Right. But a few days back I had done Archimedean property of real numbers. So there was a corollary that for each epsilon there exists a natural number n naught such that 1 by n naught is less than epsilon. Okay. So by Archimedean property we will also get another natural number 1 by n naught such that 1 by n naught is less than epsilon. Okay. But this violates this condition. This condition says that for every natural number epsilon is smaller than 1 by n. Okay. So here it violates the Archimedean property. Okay. So there cannot be any positive number inside this intersection. Okay. Similarly, you can also show that there cannot be any number of this type minus epsilon. There cannot be any negative number in this set. Okay. So there cannot be any negative number. There cannot be any positive number, but there can be this number 0, which is neutral, neither positive nor negative. Okay. So this is always there. This will not violate the property, Archimedean property, because Archimedean property is only for epsilon greater than 0. For 0, it doesn't say anything. Okay. So this intersection is actually singleton 0. Right. Similarly, what will be this intersection? Intersection of n belongs to natural number of 1 minus 1 by n to 1 plus 1 by n. What will be this intersection? So what is this intersection? Very simple. Let us compare. 1. This intersection is 1. Okay. So actually, what I have done, I have taken intervals of this type, which ultimately come to 1 in this type of interval. Okay. So if you keep on taking intersection, ultimately you will get 1. Okay. But manually we cannot do. Because this process will never end. Okay. You can keep on taking intersections. This process will never end. So when it ends, it will be 1 singleton. Okay, so arbitrary intersection of open sets may not be open. Okay. Arbitrary union is open, but arbitrary intersection may not be open. Okay. What is the time? Almost over.